Okay, so let's do R. So let's compute X to I of over Z of Z mod M, where D is some abelian group. Is some abelian group. And let's say M is greater than or equal to 2. Okay, so we know from the previous, from what we just proved, okay, so from what we just proved, so we know that X0 over Z of this thing Z mod M into this group D. So this is isomorphic to just homomorphisms from Z mod M to D. Okay, and so what this is that, so okay, so what is a homomorphism here determined by? So it has to go to a point that is an M torsion point. So a point that is, so this thing here is isomorphic to dm. So this is the set of M torsion points. You can see that if you have an M torsion point, you just send 1 to the M torsion point. Conversely, any homomorphism sends you to an M torsion point. So, yeah.
Is it similar to restricting scalars to Z mod M and D? No.
Oh, you're kind of viewing this as like an adjoint thing, or?
Maybe. You know how we can, I think that's more of a tensor product thing, actually, to restrict or extend scalars. Sorry.
Yeah, taking M torsion and looking at homomorphisms from this are the same thing, and I haven't really thought about that as adjoint functors. I guess not really, because for that thing you kind of need a tensor product. I don't know, not the way that I see it. Okay, so this is M torsion points. Okay, and so to compute the higher X, we need that was a good question though. So to compute the higher X.
Can I ask? Yeah. I think you said this, but you're saying that the map itself is to take the identity in. I missed what you said there. Sorry.
Yeah. So let's just write it out, right? So here, so what's the map here? That's a good question. You always want to write out the maps for these things. Okay, so this is the M torsion points. So you take phi, and then this goes to phi of 1. Okay, so 1 is the element here. This 1 that I'm writing is the 1 in Z mod M. Okay, so it's the equivalence class of 1. And then conversely, if you have some point in here, you can map this to like some map phi of A, where phi A of 1 is defined to be equal to A. And then this extends linearly. Okay, so there's a way to get from one of these homomorphisms to an M torsion point, and conversely, given an M torsion point, you can get one of the homomorphisms.
Makes sense.
Yeah. Okay. So to compute the higher X, we need a projective resolution, okay, of Z mod MZ or of D, okay? So, or we could use an injective resolution, but let's use a projective resolution. So here, let's write down the projective resolution. So we have Z mod MZ. Okay. Okay, so this, we need this exact sequence. And here's the resolution part. So Z just surjects onto here. And then this map here, so this is the multiplication by M map. Okay, and so so this map here takes, x and it maps it to mx, and it's a map of abelian groups. Okay, and so this is an injective resolution. So the image of this is certainly the kernel of this map where we mod out by m. And this is an exact sequence of abelian groups. Okay, so now we apply, so this is our resolution, just this little part here. Okay, so this is P0, and this is P1. Okay, so now we apply, now we apply the functor here, Hom, the functor co-represented by D, blank D. Okay, and what do we get? Okay, so so on this part here, so we get Hom Z P0 of D, Hom Z P1 of D, and then this goes to 0, and this goes to, this is coming from 0 as well. Okay, so we're only using the first part of the complex. Okay, I mean that is the complex. We're only using the first part of this exact sequence. Okay, so so this part here, and so what was P1? So this is Hamzi of Z D, and this was the multiplication by M map here. Hamzi ZD. Okay, and this thing here. Okay, so this thing, so what are our terms here? So this is like the C0 term.
You mean like the pull back or push forward when you compose with multiplication by m? Is that?
Sorry, let's see. Yeah. So it turns out that this thing. Okay, so let me just say what I want to say here. Yes, I do. But it turns out that it also is multiplication by m. So the claim here is that these two things are isomorphic to D, and that this map here is also multiplication by D. So that's a good question. So like, okay, so I have a map from Z to Z, right? And then I'm looking for maps. So this is multiplication by M. Okay, and then I'm looking at maps from here to here. Okay, so what is the map? So I have a map from, so what do I have? So I have a map from here to here, so F, right? And I called this M. So M star, yeah, that's a good start. F here, right? So this is also, I claim that this is also just multiplication by F. Okay, so this gives the M star, M here star. So what do we have? Hom Z from Z to D. So Hom Z, Z to D. And the map here is given by F maps to, so this is not quite right. So this is F composed with multiplication by M, right? This thing here. Okay, so let's look what happens here. So F composed with multiplication by M on X. This is F of Mx, which is M of F of X, right? So this pullback map is really just multiplication by M again. Okay, that's the first thing. The other thing that I want to say is that Hom, this guy here, this is really isomorphic to just D. Okay, so the map here takes F and it maps it to F of 1. Okay, so it's completely determined by where 1 is sent. Okay, so in particular, I claim that not only are these things isomorphic to D, right, but that the multiplication map, which was pullback by M, right, which is supposed to be pullback by M, is actually just multiplication by M. And it's actually just multiplication by M on D. Okay, so that's what I was writing here. So we actually have that this complex is just multiplication by M on D. And so, yeah, maybe I can write M star here. Okay, so it's like quite a simplification that we have. Okay, and so now let's try and compute bud. Okay. Okay, so now let's try and compute what homology is, or cohomology is. All right. Okay, so C0 was this. So C0. So C0 is this term. C0 is this term, and C1 is this term. Okay, so the kernel. What am I messing up here? So, oh, okay, so that's right. Yeah, so the kernel of C0 to C1, right? So this is what we so we see that this is the kernel. So this is, by the way, this is X0. Okay, let me write this again. This is X0. Let's be more precise. We already know what this is from the theorem. So we had Z mod M to D. Okay. So so this is the kernel of this map. This is the kernel of multiplication by M. Okay, and this is the D torsion. Okay, which is what we already saw, right? But we saw it in a different way here. We had to identify this with the D torsion. Okay, so that's isomorphic to the D torsion. Okay, so let's do X1. Okay, so what is X1? So this is the kernel of C1 to 0 modulo the image of C0 to C1. Okay, and what is this thing? So this is D modulo MD. Okay, so that gives us the formula for X1, and then we see that the higher X are 0 because there's nothing in the complex. Okay, and that gives us
the X1s are like the counting of the equivalence classes of extensions or something too.
Yeah, that's true. Yeah, also, yeah. So there's that other statement that these are equivalence classes of extensions, but we haven't really done that formally. But yeah, it's true that X1 classifies extensions. So by the way, this thing classifies. So we have an extension of Z mod M by D. So this is D, an extension Z mod M. Okay, so apparently the elements of D mod MD classify extensions of this form. So these are the X1s classify this. And usually there's a way to see it. So I don't really see how an element of D mod MD gives you. So for every element of D mod MD, we should be able to come up with a group, right? An abelian group that sits inside an exact sequence like this.
I'm wondering if E is just the split version, just D times Z mod M. I wonder if that like represents the identity of
That's
group.
exactly what it does.
Okay.
Yeah, that is exactly what it is. It's the identity. Yeah, that's completely correct. Yeah. Yeah. And then there's a way to do the multiplication or the addition in here. You have to do this bare sum thing. And I don't know it off the top of my head. I'd have to go look it up. But maybe I'll do that in another video. But yeah, so there's a way to have an addition in on these sequences as well, and that corresponds to sequences in this group. Okay, or the addition in that group. Yeah. Okay.
I just saw that name, bare sum, in like a history of homological algebra by Weibel. It sounds interesting.
Yeah. Yeah, Weibel has a great book on homological algebra. I think it's like the best book. So, okay. So notice that this thing is relative to this z here. We can actually change this z and get some different things. So what happens if we change the base z to, let's say, z mod m? Okay, so okay, so let's say let's take D to be an abelian group. So let D be an abelian group. With exponent dividing m, so that it is a z mod m module. Okay, so I guess I could have just said a z mod m module. Okay, that's the same thing as saying a z mod m module. Okay, so let's compute. So let's try and compute Ext. Okay, let's also make some assumptions. So let's let m equal to a times b, where a and b are. Yeah.
Sorry, the exponent of an abelian group. I feel like I should know that.
So it's the thing that kills all of them, right? So like.
So like the least common multiple of all the killers, kind of.
Yeah. Exactly. The least common multiple of all the call. In particular, this means it's a torsion abelian group. Okay. And so okay, so let's let m equal ab, right? And then let's compute. So let's compute Ext I of z mod m, and let's say we take z mod a d. Okay, so let's kind of modify this a little bit. All right. All right. So what we need to do is we need to come up with a projective resolution. So let's take a projective resolution of z mod a. Okay, let's find a projective resolution of z mod a as a z mod m module. Okay, so here's what we'll do. So we'll have z mod a okay, and there's a surjective map from z mod m. Okay, and this thing here has a kernel. Okay, so this thing has a kernel where, okay, so actually, so let's see. So this thing can be given, I guess, by multiplication by b. And then the kernel of this is multiplication by a. And then the kernel of this is multiplication by, so this is now this will be an infinite resolution. This would be multiplication by B, and this will be multiplication by A, and so on. Okay, so so let me see if this is correct. I'm worried about this step here. Okay, so that should be our resolution. So Z mod M. So I mean, I guess we could just do, we could actually just do the canonical quotient here. All right, so then this could just be the quotient map. All right, let's do that. Okay, so then you just reduce mod A. Okay, so A divides M, so this makes sense. So this is just reduction. And then if you multiply by A, right, that'll land you inside the kernel of this map. Okay, does that make sense? And then if you multiply by B, and then you multiply by A, well, then you're in the kernel of that. So yeah, so this gives a resolution. This keeps going. So this is our first example of an infinite resolution. Okay, so this is our resolution here. So this piece here. This is our projective resolution. Okay, so now we take our projective resolution, and what we're going to do is we're going to apply, so what we'll do is we'll apply our functor to it, hom z mod m blank dash to our to the resolution. Okay, and so so again, this is this is P0, this is P1, this is P2, this is P3. Okay, so we'll write it down. So we have hom z mod m P0d, hom z mod m P1d, hom z mod m P2d, and then it keeps going. Okay, and so what is this thing really? So this is really hom z mod m, and P0 and P1, they were all the same thing. So z mod m. And so this is the same thing. Z mod m, z mod m. Okay, and then the same thing goes here, right? So these are all, again, so like we had before, these are all, this is D, this is D, this is D. They're all Ds. Okay, and what were the maps? So the maps were given by multiplication by something, right? Just like we had in the previous case. So this one was multiplication, and it turns out that the pullback by multiplication does the same thing. So this is multiplication by A, this is multiplication by B, this is multiplication by A, and it alternates. Okay, so this is the first term in the complex. This is okay. So now we can start to compute. Okay, so x0 over z mod m of z mod, and we took a resolution of z mod a. Okay, so then the first one was a. Okay, so this thing here into d. Okay, so this is d of a, the a torsion points. A torsion points of D. And that's the same thing. So it also agrees if we did hom, right? So from our theorem, this is hom of Z mod A into D. And so this is the A torsion. Okay, so let's do X1. So now it gets a little bit more complicated. And let's see what this thing is. Okay, so we're in degree 1. So what's degree 1? Degree 1 is here. Okay, so it's the kernel of this map, multiplication by b, modulo the image of this map, which is multiplication by a. So the kernel of multiplication by b okay, modulo the image of multiplication by a. Okay, and it actually makes sense because a times b is 0 in this ring. All right, because this thing has exponent m, and 8m is equal to a times b. Okay, so what is the kernel? The kernel is, well, that's the b torsion. The b torsion modulo the image of a. So the a, I guess this is a, and we automatically know that, I guess, a times d. And this actually makes sense. So this is db, because every multiple of a is a b torsion element. So this is a db. Okay, so it's like the b torsion mod a. Okay, similarly, when we do x2 z mod m, it's going to be something very similar, except for we're going to have the kernel of multiplication by a, and then the image of multiplication by b. And so this thing is, well, dA, bdA. And actually, this is going to be the odd ones, and this is going to be the even ones. So this is more generally. So this for x I here, z mod a d with I odd. Oh, say this is I even. I greater than or equal to 2. And then this is the same thing for x I z mod a d, where for I odd and I is greater than or equal to 1. Because this thing just, this kind of pattern just repeats. Right, where you have multiplication by a, multiplication by b, multiplication by a, then well, I guess it's in this level here. So this is the complex. This complex here is the complex for the ext. Okay, that's the cochain complex. Okay, so now we've computed these exts. So again, the what ring? So the ring that you computed with respect to matters. That was kind of the point of this example. Okay.